Hello, this is Dan. I thought I'd make a quick video about ceramic capacitors and also try out my new camera. I'm trying a Osmo Plus by DJI. So what I'm going to talk about is the DC bias effects on ceramic capacitors. So during my day job, we are supposed to stop using tantalum. Well, in a previous job, we were supposed to stop using tantalum capacitors because of cost and also that it was a conflict material. So when you start using ceramic capacitors, you'll, instead of electrolytics or tantalums, you'll soon find out that sometimes that ceramic capacitor just does not work as well as an electrolytic or a tantalum. And that is because when you have a DC bias on the capacitor, it may change. So here's just a quick little graph. And as we can see, this is for this capacitor, a 50 volt rated cap that, as you say, for example, applied 20 volts DC across this capacitor, it would lose approximately 80% of its value. So that 10 microfarad ceramic cap may only be 2 microfarads. So a while ago I was wondering how I could measure the DC bias of a capacitor. I have a fairly nice portable little LCR meter, but it does not put on a DC bias. This is the LCR meter made by Motec, I think that's how it's pronounced, which was a manufacturer for BK Precision. It's the same meter as BK Precision 885. And I believe BK Precision a few years ago purchased this company outright. So what I ended up doing was making a little circuit, as we can see right here. And what I've done is I'll put the two, if I'm trying to test one capacitor, I'll get two of the exact same capacitors and place them here, and use a 100K resistor to apply a DC bias. And I'll put my LCR meter and I'll capacitively couple that to this capacitor that we're interested in testing. Since the LCR meter is measuring two capacitors in series, the value will be exactly half. And I put this DMM in here just to verify that the DC bias is correct on this capacitor. And for larger values of capacitors, this doesn't really seem to affect the measurement too much. So what I've done is I've made these little jigs where you can see I've got the two capacitors and the bias resistor. And I've done that for a few different parts. And so in my parts bins I'll have, I unfortunately have a bunch of ceramic capacitors that will only specify what type of capacitor they are, say like an X5R voltage and its value, but I don't have any idea on the DC bias characteristics. And on some manufacturers don't even publish the DC bias characteristics. So what we can see here is I've got, right now, I have two 47 microfarad bipolar electrolytic capacitors, and we can see that we're roughly measuring 19 microfarads. That's because the two capacitors are in series. Ideally it would be roughly 23 microfarads, but these capacitors are measured a little on the shy side, and we can see that there is approximately 19 volts DC bias on these bipolar capacitors. I'll go and turn off my DC bias, and it'll take a while to drain, but you can see as the voltage decreases, our capacitance is not really changing. So that acts like a normal electrolytic capacitor. Okay, the DC bias has stabilized on this capacitor, and we're measuring 1.5 microfarads. Since we're in series, we'll double it. We're about 3 microfarads. Now, as we look at this graph, we should roughly be 6 microfarads. So this is odd. This capacitor is measuring about half the capacitance that I think it should be. The next capacitor up to test is a X7R 4.7 microfarad 25 volt rated ceramic cap. I have the exact part number on this, but I was unable to find a DC bias curve for this exact part. So I have a generic graph that I found for some similar Murata parts, and it says, you know, that this capacitor could possibly be rated almost 80% of its nominal value at 20 volts. So we're going to take a quick peek. So right now the capacitor is measuring 2.1 microfarad. Again, these are in series, so let's double that value, so we're roughly 4.3 microfarads, which is close to the rated value. We'll apply the DC bias and see what we end up going to. Okay, now we have almost 20 volts across the part, and we've dropped to 1.1 microfarads. So if I double that, because they're in series, we'd be 2.2 microfarads. So we're roughly 50% drop from its rated value. Here's the last ceramic capacitor that we're going to look at. This is a mystery capacitor. This is in one of my parts bins, and it's specified as a 25 volt 1 microfarad ceramic capacitor. I don't have any idea of what type of material it is, and I don't have any manufacturer's part number, so I don't have any prediction of what the DC bias is going to be. But we can see that it does measure approximately 1 microfarad again. So this is half a microfarad. We double it because they're in series, so this is 1 microfarad. I'm going to add the DC bias. So now we're roughly 0.1 microfarad. Double that, so we're 0.2 microfarads. So this 1 microfarad cap is now effectively only a 0.2 microfarad cap with a applied DC bias of 20 volts. That's an 80% drop in capacitance. Anyways, that's about it. Just kind of thought I'd present how I can measure the DC bias effects of a ceramic capacitor, and you've got to be careful. Thanks for watching.